All right. So first of all, the homework's due today, so you can, if you have that, you can just put it over here. You can do after class too. I see everyone here. I guess I already started filming, so just drop it off after class, or obviously when you use late days, just slide it under my desk, under my office door rather. Today we are going to finish up talking about dynamical systems. Last time we talked about partially observable systems, and we talked in particular about observability, and also for linear systems we talked about controllability and stability of these systems. And again, these are tools that, even though linear systems are a very specialized subset of dynamical systems, they end up being quite useful in practice, not just on their own right, because some systems are linear, but a lot of times you can analyze nonlinear systems by looking at linear systems. And so today we're going to finish up talking about dynamical systems, then we'll move on to the control of dynamical systems. And in particular, we'll talk about stochastic systems. So up till now, we've really focused on deterministic systems, right? Systems where we have some dynamics, xt plus 1 equals f of xt and ut. And we assumed that that was first of all, it was known. We knew the dynamics, so we could compute those functions if we wanted to. And secondly, we assumed that this was an exact relationship. So the next state was exactly given by the current state and the current control. Now, of course, in reality, that's a very big assumption, right? That we know the systems exactly. Almost no system will be perfectly described by dynamical laws unless they're sufficiently detailed to the point where they're just too big to actually compute. And so a very common thing in practice is to add a noise element to your dynamical model, right? And so this is the definition of stochastic systems. It's systems where there is some noise term that we add to that is added to the state equations to give the next state. Now we're going to here only focus on discrete time stochastic systems. As you can imagine, in continuous time, it's actually very possible to do this too, but you need, instead of a function like this, you have a differential equation. And so you need to actually develop a theory of things called stochastic differential equations, which are just a little bit more complex, and we're not going to deal with those here. Intuitively, they're actually very simple. They're just sort of like the limit of these discrete time systems as the time steps get smaller and smaller. But there's a lot of sort of notation there that we won't really worry about here. So what we're going to talk about here are discrete time stochastic systems. And those are cases where the current state, the next state is equal to the current state and the current control, some function of that, plus a noise term epsilon t. And in general, and this is going to be a mean zero random variable. So it can have actually in general any distribution, but we will assume that the mean, the expected value of this random variable is always 0. If it wasn't 0, then you would just do actually better by adding whatever expected value it had into the function itself, and then having it be a zero mean random variable. So you don't really gain anything by allowing it to be a non-zero mean random variable. And if you do allow this random variable here to depend on the state and the control, this is actually a completely general model, right? So this could be a general, arbitrarily general distribution, noise distribution. And so you actually can encode any stochastic problem under this, if this is some function essentially of the current state or of other things as well. It's a very, very general formulation. Unfortunately, it's not that easy to solve sometimes. And the key point is why it's not easy to solve in stochastic systems. And what I mean by not easy to solve is I mean things like controllability or observability, the general case, and stability. The general case of these things all become much more complex in stochastic systems. And stochastic systems are actually ones where it's very hard to compute, say, optimal control laws for them. You know, what's the best sequence of control inputs? That's very hard to compute in a general stochastic system. And the basic reason here is that even though the expected value of this thing is equal to 0, as you repeatedly apply the dynamics model, that's no longer true. Okay, so let's say that, and this is actually not a, this is notation here, but maybe I'll try to clarify this a little bit even more. So say that x1 is given to us. We know what x1 is, and we know our control. Okay, so that means that x2 equals a function of x1, u1, plus epsilon t. Epsilon 1, I'll even say. OK? Now, if we want to take expected values here, let's take the expected value of the state. We know that this state here will actually itself be a random quantity, right? Because we're adding to the random quantity. But we could say, look for a control law that would just minimize the cost of the expected state or something like that. And in this first case, we actually can do this. We can take the expected value of x2 equals, well, this is an expectation over this thing, but that's just, there's no random variable there. This random variable is 0, so it would just be this. Okay, so that's very nice because it looks like a deterministic system now, right? The problem, though, is that if we look at the next step, this starts to break down. Okay, so now let's look at x3. All right, so x3 equals f of x2 and u2. Right? But this is also equal to f of x1 u1 plus epsilon t, and then u2. U1 here plus epsilon 2. Oh, sorry, I forgot to add the epsilon 2 here. OK. So this is all looking OK. The problem is, now if we take expectations, the expected value of x3 equals, well, this thing now is a random quantity. Right? This thing is the expected value of this whole thing here, plus this thing. Expectations, right? Expectations are additive, so you can take the expectation of the sum. That's equal to the sum of the expectations. So there's the expectation of this thing here. But the problem is, this is not equal to the expectation of just the functions being applied, again, one after the other. So x1, u1, u2, which is equal just to this is equal to this. So this is not equal here to this thing. And the problem is that when you add an expectation or a random variable inside this general nonlinear function, for a general nonlinear function, you cannot just remove that expectation here. So what I'm writing here, I guess, is just for the general case. This gets a little bit cumbersome here, this notation. So this is the derivation, but you sort of think of the final result being this thing here. The point here is that when you have when your state is some state plus a random quantity, as it would be whenever you do something like this, whenever you apply this model, and you apply the model again, the expectations no longer sort of are all nice now. You can't, the expected value of this thing is not just equal to the function itself, even when epsilon t is 0 mean. Okay, and this is just the case. I mean, this just follows from a basic fact that even though expectation random variable is 0, if you apply some function to that random variable, the expectation of that function may not be 0. Right? So for nonlinear functions, this is a big problem. And in fact, what ends up happening here is that the distribution of this thing can be really, really complicated, right? Because you've taken this random variable and you've piped it through some function such that even if the original random variable has a simple distribution, after putting it through that function, that random variable, f of something, is very complicated. So that's the problem with nonlinear systems, is that you can't just sort of compute expectations easily anymore. Even expected values, let alone the true distribution, you can't even compute expected values easily through this whole chain of states. As with everything, though, and so I guess in the general case, what you actually need to do to solve these problems is to actually maintain the entire distribution every time. So ideally, what you could do is actually have a distribution, I'll call it P of xt, that describes essentially what's the probability or probability density of being in any given state. and then you need to sort of maintain what this thing does after applying that function. And of course, that can have no closed form to it. It's not like if this is Gaussian, it will be Gaussian afterwards. It can be completely non-Gaussian then. So it's very hard to sort of maintain a exact closed form of the distribution as you progress through time. That's the basic problem with these nonlinear systems. OK, so now, as with all these things, though, there is a nice special case, and that is linear systems. Linear systems are nice for the sort of exact analysis of controllability and these kind of things. They're also very nice because linear systems with a special kind of noise term, in particular a zero-mean Gaussian noise term, those end up being systems we actually can deal with very nicely. We can take expectations, and actually even more generally, we actually can maintain this distribution over all possible states in a closed form throughout the whole time. If the noise term is Gaussian in particular, all the distributions over future states will also be Gaussian. That follows by some nice rules on Gaussians. And just to sort of see what's happening here, I guess actually this doesn't quite capture the right point, because this is true for the nonlinear case too. But let me sort of write down what I mean by this. And you'll hopefully sort of see exactly what the nice thing is here, very apparently, because it's the linearity. So if the state operations themselves are all linear, you can do the same operation you did as with the sums, but basically compute expectations in closed form for all the different states. So let's just look at expectations first. So again, let's look at a case where we know what x1 is. X2 equals ax1 plus bu1 plus epsilon 1. OK, so this will imply the expected value of x2 just equals ax plus bu, ax1 plus bu1, right? Now let's apply it again. So now let's look at what x3 is. So x3 equals ax2 plus bu2, which equals I'll even write it sort of in detailed form here. This is the sort of the same kind of chaining we did with like controllability, for example. So it's going to be a times a x1 plus a times bu1 plus, importantly, a times epsilon. Actually, maybe I won't write this out quite like this. I'll write it like this first. So this is a x1 plus bu1 plus epsilon 1 times a plus bu2 plus epsilon 2. OK? Now this is equal to a squared x1 plus a bu1 plus a epsilon 1 plus bu1 plus epsilon 2. Now, when I take expectations here, this is still all linear. And in fact, any linear quantity times a zero mean random variable will also have zero mean. So the expectation of x3 then is just going to be equal to these terms here being dropped. So it's a squared x1 plus a bu1 plus bu2. OK? And so because of this, expectations are all preserved here. This looks exactly like what the state is for a deterministic system, right? So if you had a deterministic system without the epsilons here, then you would get this being the exact equation for x3. And in this case, with a linear system, the actual expected value of x3 is exactly the deterministic value of x3 you get in the deterministic case. So essentially what happens here is that the expectations, because everything is linear, you can sort of use that rule that the expectation of the sums is equal to the sum of the expectations, cancel out those zero mean terms, and the expected values are all sort of nice like this. It actually is saying we actually can say a little bit more, and I won't prove this one because it has to do with some with rules of Gaussians. But even more than that, if this term itself is a Gaussian, then these terms will also be Gaussian. So basically, this the probability of where you are at x3 is also going to be a Gaussian. And that follows very kind of hand-wavy here by the fact that if you take a Gaussian random variable and multiply it by a matrix, that resulting quantity is also Gaussian. So these things end up being actually all Gaussian random variables. Which is a nice thing, because that means we actually can maintain in closed form the distribution over all our states at all time. This also applies, I should say, and I mentioned this a little bit last time, but this also applies to the case of linear dynamical systems that are partially observable. Okay, so let's now combine everything we have so far, really. We have stochasticity and we have partial observability. So I'll write it like this. Xt plus 1 equals a xt plus b ut plus epsilon t. Okay, and then epsilon t here is distributed normal with zero mean and some covariance sigma. And then we don't actually observe the entire state x here. What we observe instead is some linear function of the state. So we observe yt, which is equal to c times xt plus little qt, where qt is some normal random variable with mean 0 and some other covariance here. Now, I mentioned this a little bit last time, but if you remember when we talked about observability, what we were talking about there was if we see a sequence of observations in a deterministic system, it actually is sometimes possible to exactly infer the sequence of states, right? Because everything's deterministic. If you can determine the first state, you can determine all the rest of them. So ignoring these terms, right? If we can determine x1, we can determine what all the other x's are here, because we know the controls were the ones that specified those. And so we can find all the states. For a stochastic system, this is no longer the case. If you have noise either place, if you have noise here or here, the problem now is that there's just some noise terms we can never quite know. Right? So we'll always have some noise in our estimate of the current state. Especially, I mean, if we observe it, then we know exactly what it is. But if we don't observe it exactly, then we try to estimate what it is, we will always have some noise in it. And we're not going to talk about this in this class, but if you take another class on control or linear control in particular, you'll come across something called a Kalman filter. And what a Kalman filter does is it gives the best estimate of the current state given all the past observations. What is sort of the best guess we have of our current state? And that ends up being exactly actually a weighted least squares problem. You can just solve this with least squares. And so this is how you actually go about estimating your state. And virtually any system that does not have full observability will use a Kalman filter. And in fact, a lot of places where there is a nonlinear system, they still use what's called an extended Kalman filter, which is just kind of the nonlinear generalization of this to estimate the measurements. And that's not exact. That's sort of approximate in the general nonlinear case, but it still can work pretty well in a lot of cases. So that's all I'm going to say here, though. I'm not going to talk about Kalman filters in general, because it sort of opens up a lot of whole bag of worms. You want to talk about estimation and the observability of stochastic systems. So the last thing I'm going to say here, and this is before we get into control, I'm not going to say too much here about MDPs, but I want to at least mention one more type of dynamical system, which is called a Markov decision process. You may have seen these before, and what these are, I'm going to abbreviate it MDPs for its initials there. But an MDP is essentially a very general description of a stochastic system. That's how I like to think about it. Typically, though, we have thought about stochastic systems that have state spaces that are real valued, right? So I talked about, the xt being an n-dimensional vector, where each of these components is, of course, real valued. So there really are an infinite number of possible states you can be in, right? Because each component is continuous valued. The problem with this is, as I was saying before, when you talk about general stochastic equations over continuous variables, these get very complex very quickly, and they can be very, very hard to actually describe. I mean, like I was saying before, for general stochastic systems, it can be really hard to get a closed form or get sort of any compact description of this general uncertainty set that you may be in at time t. MDPs, though, are a way of representing these kind of general stochastic systems. And they get around this difficulty, typically, by actually worrying only about systems where you have a finite number of states. So normally we're talking about xt being an Rn. But for an MDP, xt is actually just a integer, really, some index that indexes which state you're in. So you can be, xt really here is in 1, 2, what am I using? I'm using n, I guess, though it's important to know that n is a different quantity here. So I'm saying there's n total states here. But whereas n before was the dimension, there were really an infinite number of total states. In MDP, there are a finite number of states. So this is an MDP framework. Similarly, we're going to talk about there being a finite number of controls you can take. So the controls, likewise, ut is in 1, 2, m. This is a much smaller set, of course, than this one. Especially, this is even smaller than Rn, right? Because Rn is still continuous value. There's an infinite number of states you can be in. Here, there's a finite number. Given this, though, a setup like this, we actually can enumerate a general nonlinear dynamics equation. And the way we do this is we represent, remember, the goal in stochastic systems was, or not the goal, but the way we would have to do things in a stochastic system to really get a full description of the uncertainty would be to describe the probability of being in any given state at any given time. But in our case here, when you have, for an MDP case, we can do this, right? Because now all we need to do to describe what state we're in is just list the probability of being in any one of these n states. So this thing can actually be represented itself as a vector in Rn. So we can compactly, or somewhat compactly at least, represent the probability of being in any given state. Right, just by listing out, and in fact, I mean, these numbers have to add to 1, so they're a subset of Rn, really. They have to be positive. But we can use a vector in Rn to describe what state we're in, or the probability of being in any given state. And we can also describe dynamics in terms of how these probabilities evolve. Right? So the way you describe the dynamics of a MDP is through what's called transition probabilities. And I'm writing these as P superscript U being a vector in Rn by n. And I'm saying n here. Really, these are probabilities, so they have to be between 0 and 1, and they have to add to 1. I think depending on what your convention, this is the rows or columns. The rows or columns here have to add to 1 because you have to make sure that this stays a probability distribution. But what this actually encodes here is the probability of going from any state to any other state given any action. So I'm writing P superscript U in Rn by n as the definition of our dynamics here. And what this specifies is this specifies the probability that x t plus 1 equals j given xt being equal to I and ut being equal to u here. Right? This is actually, so what this whole thing would be equal to, this would just be the ij entry in pu. And of course, we need u here 1 to m to specify probability distributions for what each action does. So to describe the dynamics here, we need n times m numbers, right? We need to describe them. And there's some redundancy there again because they have to add to 1 and all that kind of stuff. But approximately, you need n numbers to represent the probability distribution that you're in currently, and you need some function of m times n squared numbers to represent all possible dynamics in that system. Similarly, you can represent the cost really in any way you want. You can take you can have a cost function, which is really just a matrix in m by n or something like that, that will give you a cost to being in any given state and taking any control. Right? You don't need a functional form of it. You just enumerate all of them. And so this is typically how people define MDPs for discrete states. And they use different notations sometimes, but this is how you can define them. You can, of course, define MDPs over continuous states systems, but typically you can't really solve those tractably. You're just back to the general stochastic dynamical system, and so there isn't that much advantage to it. So typically when we talk about MDPs, we talk about discrete state things. I should add, these are very used in practice, though, right? Because there's a lot of times where even if a system really is continuous, you can get a pretty good approximation by discretizing it. By, say, taking temperature in a room, and rather than representing temperature as a real valued quantity, we don't really care, say, the difference between 71.1 degrees and 71.2 degrees. So maybe we just bin temperature into a fixed number of buckets and call that our state space. Right? Then we can take into account sort of all the possible uncertainties of what might happen when you turn on the heater. Sort of a bad example because the heater is a pretty deterministic thing, but you certainly can imagine that there are systems where there is uncertainty, yet you can also kind of discretize the state space into a pretty small number of regions, and solve the system in this case, and then things, you get a pretty good solution for that, even though you are approximating things because the true system is continuous valued. Similarly, you don't always need a real valued action space. Oftentimes, a discrete valued thing is fine, right? You can just have the heater be on or off. You don't need to have kind of fine-grained control in the middle somewhere. So those are the basic concepts of MDPs and why they can be really useful in practice. What we'll see in a couple lectures also is we will see how to solve these things too. So first we're going to take a little detour and talk about, not a detour, but we're going to first talk about how do you control dynamical systems like we've been talking about here, right? Linear dynamical systems, maybe nonlinear ones too, but we'll talk about ways of controlling those with continuous value states. At the very end, I'll take another digression and talk about how you solve MDPs, and it actually ends up being a very similar method, but it's a different set of techniques people typically use to do these things. Okay, so are there any questions about stochastic systems or MDPs? All right, let's move on then to talking about control. All right, and I'm going to take a couple steps to get to our control, where we're really going to talk about in control. And in particular, we're going to talk about 3 different ways of doing control. As I said in the beginning when we started this unit on control, our idea here was we wanted to focus on control as an optimization problem. Right, so we want to think about control as having some objective. You have a dynamical system that constrains how your states can evolve. And then your objective is to pick controls to optimize some objective function. Right? Keep the room comfortable. Keep the generators at their proper rotational angle, all these kind of things. That's going to be our objective. But before I do that, I want to talk about how control is often done in practice. And it ends up being not an optimal control law necessarily, though it can well approximate ones sometimes. But essentially, I'm gonna build control up in 3 different stages. So first, I'm going to talk about something called PID control. PID stands for proportional integral derivative, and we'll see what those terms actually mean. But essentially, if you think about controlling a room, right? I talked a little bit about how, okay, we want to control rooms to maintain comfort while the people are there, and saving energy, all this kind of stuff. That's a great way of doing control. But you know how most room thermostats actually work is they just have a set point, and if the temperature is lower than that set point, they turn on the heater, and if it goes above it, they turn off the heater, right? So there isn't much intelligence there. And this is how a lot of control actually works in practice, including control that actually does have a lot of sort of goals behind it. You just basically, if you're far away from your objective, you execute a little bit of control, try to push you closer to where you want to be. You do it kind of in a very intuitive manner. So this is encapsulated by this technique called PID control. What we're going to do then is we're going to then move to talking about a simple form of optimal control applied to linear systems. And this is going to go by the name of LQR. Which stands for a linear quadratic regulator. Don't worry about writing these down right now. They'll be in all the slides going forward. I'm just trying to give a sort of a broad overview here. Actually, I think they all will have acronyms here, so this is going to be a very uninterpretable thing on the board. So LQR, what LQR does is it says, okay, let's go back to the optimal control formulation now. But where our objective is fairly well defined. Basically, we just want to maintain the state around a given point. That is our objective. And our system is, and our cost function on that is a quadratic cost function. So we essentially penalize being away from the desired objective by a quadratic function. And we have a linear system. It turns out in this case, you actually can optimally solve for, or I should rather say, you can solve in closed form for the optimal control law. And it ends up looking not unlike PID control, actually. So this kind of connects, in some ways, optimal control with techniques like PID control. Essentially, feedback control is another term I'll use. Is where you look at the difference in your state and where you want to be, and you apply some control based on that. And then finally, we'll sort of move from these things to a slightly more advanced topic. And this is what we talked about at the beginning, though, which was really this idea of doing control as an optimization problem itself. That can be tricky if the system is stochastic, has some noise in it, et cetera. But a technique that works very well in practice is one called model predictive control, or MPC. And so we're essentially going to build from this to that to this. And I'll show you kind of why you might want to take these steps at every given time. And at the end, I have sort of a comparison between these things and the pros and cons of each. So this gives you a broad outline of what we're going to do. The first bit here will not look like optimization. It will look like simple intuition. But these things all do connect to each other. So to start off with, I guess the class was actually pretty sparse last time. So did everyone either watch the video? Did everyone that wasn't here watch the video on these equations? Because these equations are going to come up for the next several classes. So it's important to know these. These were the equations of motion for a single generator, right? So a generator is represented by a state, which I'll call theta and omega. You can also have it be omega minus the reference thing. That actually works fine, too. Theta is the power angle of the generator. It essentially captures what is the offset between some nominal voltage angle, wherever that may be. It's like in power flow, it was the slack generator, but it can be whatever we want. Captures the offset between that and the reference. And omega captures the rotational velocity. Okay, and that would be 60 times 2 pi for the US. So this is our state. And the way we're going to describe the dynamics of the system is with a differential equation. It's a linear differential equation. So this is saying that, well, the derivative of our power angle is just going to be omega minus omega ref. And here I actually will have these two be my state. And so omega ref is sort of a constant you add afterwards. But you can do it either way. You can either have your state be omega minus omega ref here, or your state just be theta and omega. It doesn't actually matter. It doesn't affect things. Then the equations, so this describes how theta evolves. And this is very sort of definitional even. The derivative of angle is angular velocity. But we're talking about how far it differs from, a fixed point that doesn't matter, where in the rotation we are. So we actually have the derivative be omega minus the reference velocity. Because essentially what this captures is if our generator is going too fast, if it's going at 61 hertz, actually that would be really, really fast, but going a little bit over 60 hertz, our power angle will start to increase. And if it goes under 60 hertz, our power angle will start to decrease. That's the intuition here. The second equation of motion here is just essentially the mechanical, the interchange between mechanical and electrical power on the generator. So the generator itself has some inertia. So if you turn off all power, or essentially actually, if you put a huge load on it, say if you turn on some huge load, it won't immediately stop spinning. It has some inertia, but it'll start slowing down because it's not generating enough power to actually keep up with that. And the equations of motion here are 1 over 2h, where h is called the moment of inertia, it's just some physical constant, times the power mechanical minus the power electrical. Okay? But the mechanical power in this case really is our control input. That's what we can decide to do. We can open up some more valves and pour more water on a turbine spinning, for example, or open up more valves in a gas turbine and inject more fuel into it. That's the control input we have. So really our control input here is U. P elec is, in general, will actually be determined by power flow equations. This is what I talked about when I talked about differential algebraic equations. These will relate to all the generators, and we'll get back to that in a second. But for here, let's just talk about a single generator. So you can just think of this as being some fixed quantity. It's whatever power people are actually using, whatever electrical power people are actually using from the generator is just P elec. Okay, so these are our equations of motion for a generator. Now the question is, suppose we have some goal. All right, and I'm going to say that our goal in this case is to keep the angle of our system, and I'm going to use superscript d here to denote desired. So theta desired is equal to 0. This is our goal. We want to achieve that if we're not at 0 yet, or maintain it if we already are at 0. So now let's sort of talk about how we might do this. Well, the first thing to notice is that if we already are at 0, so if suppose theta is equal to 0, theta changes as a function of omega minus omega ref. So so suppose that theta equals 0 and omega equals omega ref. Okay, so suppose we start off with this. Well, then I can tell you exactly what control to apply that will keep this thing there, right? Namely, you want to make sure that omega doesn't change. This is OK, right? Because this won't change. As long as omega equals omega ref, this thing won't change. And so you want omega to be not changing. So you want omega dot to be 0. And that will happen when U just equals P electrical. Okay, so let's just take U to be P electrical. And what we see is that this can work. OK, so if we start off at the right velocity and the right power angle, everything's good. We stay there. Of course, and I should mention this seems sort of obvious, but this is actually a term called feed-forward control. Basically, we take the thing, the control input, that would keep us at the right point if we're already there, and we just apply that. And so I'll refer to this term, like an additional term you add to your control, as always being a feed-forward term. I should say, if I ever slip and sort of say things like feedback or feed-forward without sufficiently explaining them, just interrupt me. I will try to explain all these things, but sometimes I slip and use this notation without explaining it enough. So this is called a feed-forward term here. Means we just take, we don't look at what the state is at all. We just take what we hope it is and just apply the control that would do well in that case. Now, of course, the downside here is that what if omega is not equal to omega ref to start off with? Even suppose that theta equals 0 to start off with, but theta does not equal omega ref. Then this thing will still be 0, right? So we're still not changing omega at all. So omega minus omega ref will be a constant. This is what's being shown in the second graph here. So this shows time. The red dotted line shows omega minus omega ref. And the blue line shows the evolution of theta. So what's happening here is that we are behind our reference. We are behind the reference angular velocity here. And so because of that, well, theta changes according to this difference here. This difference is always, in this case, negative. And so theta will keep just decreasing. Even though we're applying the right control in some sense. We're applying the control that if we were at the optimal solution would keep us there. If we're not at this point, then this still does maintain 0 change in angular velocity, but we just actually keep doing worse and worse. So this is kind of interesting, right? Because even though we're applying mechanical power that's equal to electrical power, we actually are systems kind of breaking down. Right? This now motivates something called feedback control. And the idea is that we don't want to just look at what we should do kind of in our best hypothesized mind, saying suppose everything's great, what should we do? We also want to look at what's actually happening and make adjustments based upon that, apply either more or less power to kind of catch up and get where we want to get. I also should add that maintaining a fixed power angle is not the most common control task in real generators, really because oftentimes you don't really care about your absolute power angle. What you care about is maintaining good angular velocity. So oftentimes actually people just do control for angular velocity. They don't worry about the absolute angle, other than maybe to a certain extent to make sure these things don't get too far away. But we are going to talk here for sort of illustration purposes about maintaining angle. Just know that's not that common of a real task in a lot of power systems. It's sort of one that we're using here as an example. So anyway, let's talk about what we could do to do better than this. And the first guess is going to be to say, well, okay, we're saying that ut that equals p elect, okay. But if theta is getting less than our desired theta, we probably want to apply more power, right? We probably want to actually apply more power so that maybe we start increasing the rotational velocity. That starts increasing theta again, and so that sort of makes things a little bit better, right? So let's look at the difference between theta and theta d. Actually, I want to make sure I have I'll write it here, but then I might need to have a different sign on the next. I forget if I had this ordered this way or the other way on the next slide. Doesn't matter. I just change the sign of what kind of control you apply. So anyway, let's look at whether we are above or below our desired position here, or our desired power angle. And let's apply some control based on that. So let's take this, and then let's just multiply. Because the units here might be different from the units here, let's just multiply it by some constant, which I'll call Kp. I suspect actually I have it ordered the other way in the next slide. Yeah, I do. So let me just go in slides. That's just to keep things positive. In the other case, Kp would actually be negative. Here, Kp would be positive. So let's look at the desired thing, which is actually fixed, so I won't put a t here. I think I have a t there, but whatever. Minus theta t. And in this case, actually, this thing is not only fixed, but it's also always 0. So we can just write this as P elec plus Kp, or rather minus Kp times theta t. All right, and what this does is this says, OK, I'm going to change the control input I apply now based on how well I'm doing here. So if, and this notation, I should say, Kp is positive, right? So if we fall behind, if this desired angle, which is 0, gets, if we start falling behind that, this thing will be positive then. And so we will apply additional mechanical power to kind of help. Well, what happens, of course, right, is that the mechanical power will speed up the system. The system starts going faster. And that will gradually start bringing the power angle back to 0. Similarly, if this is too big, then we apply less than the electrical power, and that kind of lets the angle drop back. And so this works OK. It sort of kind of works. But what you see is what happens is this. So unlike before, so again, this plot here shows the blue line is theta. That's our power angle. We want to keep it at 0. And the red dotted line is the rotational velocity of the turbine. I guess gas turbine or whatever, generator, spinning generator. Actually, that minus the reference velocity. So something really kind of unfortunate happens here, though, which is, you can sort of think of this as a two-stage process, right? So remember our equations of motion. Theta dot equals omega minus omega ref. Omega dot equals 1 over 2h u minus p electrical. OK, so what happens here is this term is less than its desired amount. As long as it's less than, I'm going to just show it here. So it starts off less than the desired amount. So it's less than the desired amount, and initially that's happened, say, because this is too low. All right, so we start, this thing is negative, and so it's less. This has become less than the desired amount. So now this is too low. So we start adding more power here. Right, we start applying more mechanical power. And what this does is this starts increasing our rotational velocity. So right from the beginning, this is our rotational velocity, and we start increasing that. And as long as theta is still less than what we want it to be, we will keep adding more power. Or sorry, we won't. I mean, we might add. This might be closer and closer to this one, but it will still be more than that. And so we'll still keep increasing the speed of our generator. So the generator speed keeps increasing. It doesn't actually reach the desired desired angle until this point here. About this point, about 1 second in, or a little less than 1 second, we reach an angle of 0. Now, of course, by this time, we've already sped up the generator a lot. The generator speed is going much faster than it's supposed to. And now we have the other problem, right? The generator is going too fast, faster than it should. We have the right power angle for a second, but the generator is going too fast, so our angle starts going too fast the other way. It starts creeping back up. And then we do the other things, right? Then we start applying less power than mechanical power. We start slowing things down, but again, by the time we've reached our 0 again, we've slowed things down way too much. And you have this, there's exactly sort of sinusoidal oscillations is what you get here. You get these sinusoidally oscillating things where the system just, tries to maintain this, but by the time it actually gets there where it wants, it's slowed the system, slowed the generator down too much, so it's going to keep going. And in the ideal case where there is no friction, so nothing sort of naturally slows down the generator at all, this will just oscillate forever. And that's true whatever value of Kp you choose. Higher values of Kp will keep theta closer to the desired amount a little bit, but it will actually make for bigger oscillations in the angular velocity. So you can keep this pretty close. I mean, you can imagine, right, if you really are extreme here and do put a lot more or a lot less power in based on this thing, you could probably keep this thing closer, but that actually will come at the cost of huge variations in the angular velocity. And so you typically don't want to just do this. It would be a really bad idea to have your sort of generator always having either the rotational velocity too low or the or this too low. Rotational velocity too low or the angle too low or too high, or the angle too low or too high. You never actually reach the desired location here of zero power angle and angular velocity being equal to the reference velocity. So what this motivates is another element. Is okay, well, the problem here was sort of silly. It's that we only tried to match the desired angle. There's another sense in which we want to match two things, right? We want to match the desired angle, but we also want to match the desired rotational velocity. Okay, so let's add another term here that says, let's also, I won't write the constant yet, let's also look at the difference between omega and omega ref. And again, I think I should flip those in the notation here. Let's look at omega ref minus omega. And apply some force based on that. And of course, these things, though, are really, this is just the derivative of this thing, so we can represent this in terms of the derivatives too. So, but let's just look what it actually does. So what we also have here is we have, and then you can write it both ways. You could either write this as omega minus omega ref, or you could write it as the desired theta dot, which is just omega minus omega ref, versus the actual theta dot, right? So the desired theta dot is actually 0. And the desired theta dot is just, so the actual one is 0. The actual one is omega minus omega ref, the desired is 0. So you can also write this just like this, like I wrote up here, as kd times, I probably won't quite be able to see that in the video, oh well. I'm writing exactly within the slides, so it doesn't really matter. Theta dot d minus theta dot t, and that just equals this thing here with a minus sign. Okay, and what this does is says, okay, let's try to match two things now. Let's match both the desired absolute angle. Let's also match the derivative of the angle, namely 0. And if you've sort of taken any physics before, this is also sometimes called like a drag term. So we're also, effectively one thing that you can interpret this as is applying a sort of hypothetical drag force that will kind of slow the whole system down. Doesn't want to be moving. We don't want this to have a derivative here, so we kind of apply something that acts in opposite to its derivative. And so we try to sort of resist the motion of these things and slow them down. And it turns out this actually does do what we want in some sense, right? This actually does work. And so you will frequently see PD control as actually something that's really used in practice. You will also, right, I should mention, these terms, this term here is called the P term, stands for proportional. This term here is called the D term. We'll get to the I term in a second. But you will rarely just see P control. You may see that sometimes, but usually it's only for systems that already have essentially a built-in kind of drag where you don't need to do this. You will frequently see PD control when you need to control both an angle and maintain it at sort of some desired or usually 0 velocity. And this actually also has a feed-forward term here in addition to the P and the D terms. So this works. This is a plot now of starting in the same position as last time. So I actually start, I'm not quite sure where this is in the cycle, but it's some initial angle not equal to 0 and some initial velocity not equal to 0. you apply this control, and pretty quickly the system will stabilize to its desired position. It'll have power angle 0 and angular velocity equal to the reference velocity. Now there's one issue which is going to come up a lot, which I've kind of slipped under the rug so far, and it's going to come up even more actually in the next slide too. But those, all of a sudden, I mean, I've written these things down. This all makes sense, but I've also just written these constants here, right? Kp and Kd. And I didn't really say what those are. It's just kind of something, right? You take the difference and you apply something to it. You multiply by something. And that's because, well, you know, the units here are not at all the units here. And the scales could be different. I mean, if this is angles versus radians, you're going to have a completely different scale. It's all valid. You just need to scale it differently. And so the choice of these terms, which are called control gains, that's somewhat of an art, I would say. There is some sort of scientific way of doing this. And actually, when we talk about the connections between LQR and PID control, I'll sort of, hopefully those will come in a little bit more. But really, you have to pick them. And you have to just pick them somehow. So that's what we'll leave it at for this time, I guess. Just pick them. And as you see, different gains here do different things. So if I have a bigger D term, it looks like I kind of reach it a little faster, for example, here. Now, it's important, though, that the controls you apply, right? So in some sense, bigger gains are always better because they will make you reach your desired position faster. And if you have enough D term, which is essentially a damping term, then you actually will, you know, and you can keep raising P, and it'll just make you reach the desired point faster and faster. So that sounds great. The problem, of course, is that you're going to start applying really, really big controls, right? So this is our dynamics here, right? If all of a sudden, you know, you're told to apply -2 megawatts, your generator, well, you can't really do that, right? And the most you can do is sort of shut it off. You don't really want to have the need for also turning on load at your generator. And a lot of things actually will do that by default. They'll sort of, depending on the gains, they can actually prescribe actions that are outside the range of what actually is achievable. So there's a lot of trade-offs when it comes to choosing these gains. You have to make sure, you know, they're the right size, that they get the desired. And the other thing I should say is that, you know, in the ideal kind of continuous time case, these will always be changing exactly with the system here. But if you just do it in discrete time, if you have some actual computer controlling these things, then you know you can't be reading instantaneously the actual differences here all the time, and so you might actually end up applying control that's a little too much for what it is right now, and then basically these things can quickly get nasty. So it's kind of an art. We won't talk about it too much, but you'll play a little bit with some kind of controllers on the homework. I should add, the homework's going to be out next Tuesday. I wanted to get through all of this and the LQR stuff before giving up the homework. So it's due next Tuesday, and it'll be due 2 weeks from then. OK, so that looks good. But the problem is, it's still assumed, all of this, I should say, everything I've done here so far, assumed that we knew this term. So remember, our equations are like this, and they're sort of very explicit. There is the fact that P elect, if you set U to be equal to P electric, then this is going to be 0. But what if you don't know what P electric is beforehand? I mean, right, that seems pretty possible, actually, that, you know, I don't know if someone's turning on a light and, you know, far away. I don't want to always have to be asking them that. That will determine what P electric is. So how do I know what control to apply? Now with this lead, and maybe you can take a guess sometimes, but what this leads to is if you don't take a guess, you actually still can apply PD control. You can set this to be 0 essentially, and still do these two things. And that kind of just reacts to the situation, right? What that would say is, OK, you know, I'm going to not put any. I'm going to essentially assume I don't know what my electrical power I need is. I'm just going to let the system tell me that, right? Because we know that if we're not producing enough, then we're going to start falling behind. And sort of this control law here already accounts for things we can do to not fall behind or not speed up too much. So I'm just going to apply that. I'm just going to apply this part here without p-elect. That's actually a very reasonable way of doing things. The problem, of course, is that you will never actually reach your desired state now. Right? This is what happens if you execute just based upon these rules here without a p-elect. And what's happened here is that the velocity achieves 0, and we know that because the angle is not changing. It's fixed. But the angle never achieves its desired value. It's always a little bit below 0. So that seems like a bad thing, because we've never actually achieved what we want to achieve. What this does then, what this motivates then, is another term we can add here. And this other term says, well, let's look at this difference. Let's look at how far away we are. Let's start by just applying PD control without any feed-forward term. Let's start by just doing this. I should erase it in both spots. OK, let's start off by doing that. That'll get us somewhere. Maybe we wait a little while to make sure we're not make sure everything settles first. So we wait a little while, everything settles. And then we say, OK, there's some error in our system. Let's look at that error. Let's look at not just kind of the current error, but let's look, because the current error we're already sort of looking at, right? We're already looking at the current error here. Let's take all the past errors we've seen so far and add them all up and apply some control based upon that. And the idea is if we stay far away from where we want to be then we're going to keep adding more and more to this sort of accumulator here. And we'll keep applying more and more control until eventually we hopefully reach the desired position. And this is called the last thing, which is the PID, which is the integrator term. So what we're going to do, I'll write it first. What we're going to do is we're going to take all of our errors here, not just the one at the current time, but we're going to take the sum from tau equals 1 to t of theta d minus theta, I'll write it like theta d tau, even though in our cases they're all the same. Theta d tau minus theta tau. Because I kind of messed up the vertical alignment there. The sum from tau equals 1 to t of theta d tau minus theta tau plus this, and I'll erase this subscript here since we don't actually have a time-dependent desired position. And also and then we're going to multiply by something else, by some other term here, which I'll call ki. And this is the I term, which stands for the integrator term. You can imagine in continuous time, this is not a sum. This is actually an integral over these errors. And again, you can simplify this a little bit by just leaving out, because we know that the desired location is always 0. You can leave that out. So that actually, now altogether, this works quite well. So I'm showing now for some parameters here, k and some parameter ki. Importantly, ki should also depend on the time delta, right? Because we're adding these increments, but if we increase our time, or if we decrease essentially the delta we use to specify our discrete time steps, we also want to decrease k because we're adding a lot more things now. So we want to do it like this. And so ki should somehow depend on delta t. So here I'm using ki as 15 delta t. So that's sort of the scaling that you want to use for ki. What this does is this builds up over time, looks at the errors we're getting and builds up. And if you sort of tune these right, then this term ki times this thing. I'll just write it out. So I wrote also there, this equals ki times the sum from tau equals 1 to t of theta tau. And I think that I had them all, the conditions all were negative there. If you do this right, this will converge to the solution where you have both, you achieve your desired angle and your desired reference velocity. And of course, what that means, what that has to mean, is that this thing here will go to p elec. So even though we don't know it beforehand, by looking at our errors over time, this whole term will go to p electric. And it has to, right? Because otherwise it couldn't. I mean, that's the only way things can be balanced. So this term has to go to p elec. What's very interesting is that this happens for a wide range of different ki's here. And what happens there is, depending on what you choose for ki as you evolve in your history, or depending on what you choose for ki, as you evolve through states, this sum of errors will change. Right? So it's sort of very, very nice here. What happens is that this sum of errors adds up to whatever you need it to add up to, such that ki times that sum equals p elec. But I mean, that sort of sounds kind of amazing in a lot of ways, but really isn't that amazing. All that's happening, I mean, it has to, right? Because all that's happening is that you're just looking at the steady state error you have, and you're either increasing or decreasing your counter based upon that. And if you have a bigger ki here, then you would naturally get to it faster, maybe. So your counter doesn't add up to quite as much. But the only sort of fixed point here will be when this whole thing equals p electric. So that's the basic idea of PID control. These, as I said, some terms which are frequently used are feedback versus feed forward. So feedback here means that we're taking our actual state, we're looking at the state, and we're feeding back to determine our control based upon that. So these two terms, the P and the D terms, are often called feedback controls. If we just have a p elec here, that's called a feed forward control. And the I term, actually, people can use both those terms for it. It's sort of a feed forward because at the end, this is ideally a fixed number, so it's sort of acting like a feed forward term. But it also is feedback because it's taken into account sort of all that we've done so far. So it's kind of both. But so don't worry about how we designate that. These two terms are called feedback terms. The p elec, if it's fixed, is called a feed forward term, and this term is the integrator term. It's really neither. Or both, if you want to think of it that way. So this is sort of great because what we've done is without, I mean, I didn't mention optimization at all here, right? I didn't talk about optimization. I started with talking about controlled optimization, but now I'm just talking about numbers that you multiply by other numbers, by errors to sort of achieve what you want to achieve. And it turns out actually that if you have a linear second order system, this means that there's two differential equations, and your system's all linear, then it actually turns out that PID control is optimal without you even knowing it. And what I mean by that is there is an objective that PID control is optimizing. But oftentimes it's actually harder to know what it is than just to specify gains like this. The flip side, though, is that this is a really sort of simple system. I'm just talking about a single generator here with a simple one objective of just maintaining this at some reference position with 0 or with angular velocity equals the reference velocity. And so that actually is kind of a simple case, really. It seems obvious what to do, right? You just apply the controls based on what you see. When you have a multivariate system, this is a system where you have many different generators, say, now, and each of those can apply whatever power they want. And say you want to maintain a certain set of angles now based on some power flow computations, something like this. PID control can be a lot trickier. But the amazing thing is that even though there's no real reason for it to work in that case, I mean, you have lots of different control elements. They all can be doing their own thing. They're all related and interconnected through power flow equations. the amazing thing in some sense is that PID control actually can still work pretty well. So sometimes even when you do have a multivariate system, PID control is no longer optimal, but it still can work pretty well. So to talk about that, the last thing I actually won't get to probably PID control today, but what I want to talk about is the equations of motion we're going to use to describe a multi-generator system. So before we're talking about one generator, now we're talking about lots of generators. And in particular, we're going to talk about this using the DC power flow approximation. So we're going to combine this thing here, which is called the swing equation. This is how a single generator evolves, with DC power flow, which talks about how the angles of these things have to be related to the electrical power, right? Because those have relationships for a big network. That's exactly what you solved in the homework. So okay, let me just hopefully I'll get through this today, and then I can maybe go through it again next time. But I'm going to cover the basics here. So our system of what we want to do now is we want to derive a system of equations for how generators, how their power angles and rotational velocities evolve, subject to the fact that these actually are connected. There are grids here, and they also obey power flow. So remember what you saw, so we're going to write a few things. First of all, we're going to write each generator itself is going to just obey the swing equations, right? So now we're going to have I not just being, we're going to have not just one, we're going to have several of these. Omega I equals 1 over 2 HI. They can all have different moments of inertia. They each have their own control input, and they each have a power. An electrical power, and this is for I in all our set of generators, using the same notation that you use for the homework there. Next, we also are going to have the DC power flow approximation, which says that P, and this is the same, importantly, this is the same P and the same theta here, P equals B times theta. In the homework, you did DC power flow in the homework. Actually, there was a negative sign here, but we can just incorporate that into the B matrix itself. So I'm just going to write it like this for the rest, just to keep things a little simple. OK? So those are our equations. This now is a set of differential algebraic equations, right? Because we have, oops, sorry, these are time derivatives here. We have differential equations that specify how certain states evolve. And then we have algebraic equations. So remember when I talked about differential algebraic equations last time, for AC power flow, there are various things that were determined by controls, various things that were determined by the system itself. Some things were determined by, what maybe that is, some things were determined by differential equations, and some things were determined what they had to be by the algebraic equations. So in particular, what variables here would be the differential state variables? Those are the ones that are given by differential equations. If you don't have the slides in front of you, maybe it's actually hard to guess if you don't have the slides in front of you. Sorry, the differential state variables are those things that are given by differential equations. So really, it is just this theta I and omega I for I in the generators. Those just almost by definition are state variables. The algebraic variables are everything else. That's what's determined by these things. And then I should also add, these also have powers and such for the loads too. It isn't just for the generators. There's also powers and angles for the loads. Okay, so these are our variables for these are all state variables for these two equations, and then our algebraic variables. Well, that would be, we have theta I and theta I for I in the loads, right? Because we don't know what those are ahead of time. Those are only determined by this thing. And then all of our PIs, PI for all I. would be our algebraic variables. And we can make sure we have the right number of them here because, let's see, these, they are going to be 2 times the number of generator state differential equations here. And then they're going to be n, where n is the total number of nodes, algebraic equations. So we better have 2gen plus n total variables. Oh, actually, and we don't. Look at that. So here's an important point too. So the loads, the power at the loads does seem to be fixed. So this is actually just for the PI for the I and the generators are actually the ones that we care about. Because the loads are actually fixed. Those are known. They seem to be known. So look at that. I caught myself by just counting variables there. It's a good thing to do. And now, of course, we do have we do have n of these because we have n. This is one for each load, and this is one for each generator. OK, so now this is a differential algebraic equation, but it's this nice case I mentioned before, where the algebraic equations are linear. So what we're actually going to do is it's kind of a pain to work in this direct representation here. This is, how do we integrate this forward, for example, while maintaining these things always being satisfied? It's actually kind of a pain. What we're going to do instead, actually, is we're going to eliminate the algebraic variables and then write everything in terms of the differential variables. And we can do this because we have n equations and we have n algebraic variables. So we can eliminate them using this equation here. So importantly, our algebraic variables here are our theta i's at the loads and and the power at the generators. And so we want to eliminate those from the equation itself and just write them in terms of algebraic of differential equations. Okay, so I don't think I have time to do that quite now. It's a little bit of a derivation, and you will have to do this again, sort of for this actual systems on the homework. So I'll stop for now. But actually, first, are there any questions about sort of the general procedure here? OK, in that case, I will stop here, and then we can chat next time about how do you actually go about eliminating these things and writing everything in terms of just differential equations. All right.